Welcome to Calculus. In this first video, we're going to introduce you to calculus by describing a couple of the problems that led us to develop calculus. And one of the big problems that mathematicians had that led us to develop calculus was called the tangent problem. And this is how we want to determine the slope of a line that's tangent to a curve just at one single point. And then the other problem was called the area problem, which is how to determine the area under a curve. In this video, we're going to start off by talking about the tangent problem. Now, in order to discuss the tangent problem, we need to do a quick review of average rate of change. And if you recall, the average rate of change is the slope of the line that passes between 2 points on a curve. And so if I'm looking at the interval, let's say generically from A to B, and I want to find the average rate of change from x equals A to x equals B, then we would take the corresponding y value for B, which is f of B, and we would subtract the corresponding y value for A, and we would divide by the difference in the x's, which would be B minus A. This represents your change in y. This represents your change in x in the denominator. Now, when we look at the average rate of change of a line, which we have 3 examples below, when we look at the slope of a line between any 2 points, that slope is going to be the same. Whether I pick these 2 points here on the first graph, that's going to have a slope of -2 because I go down 2 and over 1. And then if I pick another 2 points on the graph, let's say I pick these 2 points here, I'm going to go down 4 and to the right 2, but that has the same ratio of -2 because -4 over 2 is -2. So it doesn't matter which 2 points I pick, I'm always going to get the same slope, which in this case is the average rate of change, right? The change in y over the change in x. And it happens, the same thing will happen for the next line, right? No matter what 2 points I pick, I'm going to get the same ratio between the change of x and the change of y. Now for a constant function, for example, h of x is equal to 2 in this third graph, for a constant function, the average rate of change is always going to be 0 because the change in y will always be 0 no matter what the change in x is. If I look at the change in x between these 2 points, that's a change of 3 units, but my y value hasn't changed. I just went straight across. I haven't gone up or down at all. So my ratio is going to be 0 over 3. And no matter what's on the bottom, as long as it's not 0, 0 over something is going to give you 0. So for a constant function, your average rate of change is going to be 0. Now, if we pick a curve like x squared, depending on what 2 points I pick, I'm going to get a different average rate of change. If I call this line number 1, and I pick x equals 1, and x equals 2 as my interval, my rate of change, I should say average, I'm going to abbreviate average rate of change, ARC, for line number 1 is going to be, I'm going to go up 1, 2, 3, and over 1. So I'm going to get 3 over 1, which is 3. Now if I pick a different 2 points, let's do this in a different color so it's easy to see the difference. Let's say I pick this point and this point, and I try to find the average rate of change from -2 to 0, right here, -2 to 0. I'm going to go down 1, 2, 3, 4, and over 2. So that rate of change on the interval from -2 to 0 is going to be -2. So when you have a nonlinear function, your rate of change is going to be different depending on what 2 points you pick. Now this led to calculus. Someone said, well, what if we want to find the rate of change, but just at specifically 1 point? I don't want it at 2 points. I just want it to touch the curve in 1 point. Well, in order to find the rate of change, okay, we need to do it over 2 points so that we can take the change in y and then over the change in x. So how would we figure this out if we're only doing it at 1 point? So what someone came up with, if I want to, for example, find the rate of change at, say, 0.5, specifically just at 0.5, someone said, well, what if we pick points and we estimate it by finding slopes as it gets closer and closer to 0.5. So someone took the slope of this line and then they moved closer to 0.5. Then they found the slope of that line and then they moved closer and closer until they got so close that you could estimate really well the slope that touches at just that 1 point. Oh, this is how limits came about, because they're trying to find the limit as the change of x became 0, right? The change in x got smaller and smaller and smaller because those 2 points were getting closer and closer together. So they call that finding the limit as the change in x approached 0. So notice as I slide this point here, so the difference between those 2 points, the blue point and the green point right now, is 0.485. And then as I move that point closer, that change in x gets smaller and smaller as I approach overlapping points until it's 1 point and my change in x is 0. So we call that the limit as the change in x approaches 0. So now, using that idea, we are going to find the slope of the tangent line of f of x is equal to x squared at the point x equals 1 by finding the slopes of secant lines and getting closer and closer and closer to that point x equals 1. And that change of x is getting smaller and smaller and approaching 0. So the first point that we're going to use is 2, 4. So we're going to use the point 1, 1 because that's the point we're trying to approach, and we're going to start with the second point at 2, 4. And then with the part B, we're going to move closer by going to 3/2 and 9/4. And then point C, we're going to get even closer using 5/4 and 25/16. So for part A, let's draw this on the graph. Here's the point that I'm trying to find for the tangent line, the slope of the tangent line. This is what we're trying to find, is that the slope of the blue line. So for the first line that we're going to use for our estimation, we'll do this one in green. I'm going to use the point 2, 4. So I'm going to go over 2 up 4. So here's the slope of the line that we're going to find for part A. Okay, so when I find the slope of the line for part A, I'm going to take the change in my y's, which is 4 minus 1, over the change in my x's, which is 2 minus 1, and that's going to give me 3. Then I'm going to, for the next point, let's do this one in pink. I want to do the point at x equals 1 1/2, 3/2. So I come over to 1 1/2. Now I'm using this point in my x equals 1. And I'm going to try to get a closer estimate to the slope of the blue line. So for this one, I'm going to take the change in my y's, which is 9/4 minus 1 over 3/2 minus 1. And that's going to give me 5/2, which is 2.5. So that's going to be the slope of the pink line. Now I'm going to pick another point even closer, 1 1/4 instead of 1 1/2 now. So that's 5/4. So let's do orange. So now I'm going to pick this point here. Now I'm trying to find the slope of this line, which is getting closer and closer to the slope of the blue line, which is what we're trying to approximate. So to find the slope of the orange line, which is the closest line so far that we've got, we're going to take 25 over 16 minus 1 over 5/4 minus 1, and we're going to get 2.25. Now notice that I started at 3 and I went down to 2.5, 2.25. We would say the limit as the change in x approaches 0, because the change in x, which would be 2 minus 1, then 3 1/2 minus 1, then 5/4 minus 1, that change in x is getting smaller and smaller and smaller. I'm going to approximate that gets closer and closer to 2. That is my guess. If I added a fourth point, and I called it 1.01, and then whatever the corresponding y value is, and I found the slope of the line that passed through that point and 1, 1, now my change in x would be 0.01, right? The difference between 1 and 1.01, again, is getting smaller. Now it's 0.1, and we would get an even more accurate picture, more accurate estimation of the slope at just the 1 point. But given the 3 values that we have here, I'm going to estimate that my slope is 2 at just that single point, x equals 1. Okay, so now that we're going to continue exploring the differences between average rate of change and instantaneous rate of change at one specific point, we're going to now apply this to average velocity and instantaneous velocity. So your average velocity is just going to be the velocity over a specific time interval. So if we think of s of t as your position function, and t is your time, then your average velocity over a time frame, let's call it between A and B, V sub average, you're going to take the corresponding position value when you plug in B into your position function and subtract the corresponding position value for your A value, and then you subtract the difference in your time. Let's say you want to find the instantaneous velocity at a specific point A. Then as you pick your points so that your time value is getting closer and closer to A, as you pick those points closer and closer to A, you're going to approach the instantaneous velocity. So as the values of t get closer to A, you will approximate the instantaneous velocity. Now let's walk through an example. We have a rock that is dropped from a height of 64 feet, and it's determined that its height in feet above ground t seconds later is given by the position function negative 16t squared plus 64. So what that means is if I plug in the seconds between 0 and 2, it will give me the position above the ground in feet. So it says find the average velocity of the rock over each of the given time intervals, and then we're going to use this information to guess the instantaneous velocity of the rock at time 0.5 seconds or a half a second. So this is the time 49 seconds, and then we have the time 0.5 seconds. We need to find the corresponding value so we can find the average rate of change over that time. So we're going to find the position at 0.5 and subtract the position at 0.49, and we're going to then divide by the difference in the time, so 0.5 minus 0.49. When we plug that all in, we're going to get negative 15.84, and because we're using feet and seconds, this will be feet per second. Okay, now really the speed of the rock is 15.84 feet per second, but the negative just indicates the direction that the rock is moving. Okay, now let's do the same thing for this time interval. We're going to do it from 0.5 seconds to 0.51 seconds. So we're going to find the position of the rock at 0.5 seconds, and we're going to subtract the position at 0.51 seconds, and then we're going to divide by 0.5 minus 0.51. When we do that, we're going to get negative 16.16 feet per second. So the instantaneous velocity has got to be somewhere between negative 15.84 feet per second and negative 16.16 feet per second. So a good guess for an instantaneous velocity at 0.5 seconds, just at that one instant, a good guess would be probably negative 16 feet per second. All right, so now that we've talked about the first key problem that helped develop calculus, which was the average rate of change versus the instantaneous rate of change, now we're going to get into the second key problem, which is finding the area under a curve but above the x-axis. And so if we look at this picture here, this first one, we want to find this shaded area. Now there's no particular formula for that specific shape. If it was just a rectangle or a circle, we have formulas for those. However, this is an irregular shape. So to approximate the area under the curve, we use rectangles. We create rectangles and then we add up the area of all the rectangles. Now this will only give us an approximate area under the curve, but the idea of the limit gets introduced into this scenario because we've discovered that if I make the width of that triangle, we'll call it delta x because it's the change in the x from this point to this point. If we make that change smaller and smaller, and the rectangles will get smaller and smaller, and the area under the curve will be approximated closer and closer to the actual area under the curve. So let's walk through an example. We're going to estimate the area between the x-axis and the graph of x squared plus 1 over the interval 0 to 3. So what we're trying to do is estimate this highlighted area in pink here. This is 0, 1, 2, 3. And we're trying to find the area under the curve between 0 and 3. So we're going to use these rectangles to give an approximation. So I'm going to find the area of each rectangle and add it up. I'm going to call this rectangle 1, rectangle 2, and rectangle 3. Rectangle 1 has an area of 1, because this is 1 unit here and this is 1 unit here, because the area of a rectangle is length times width. Now I'm going to do the same thing for the second rectangle. The area of the second rectangle, I would have to know the length times the width. The length is going to be 2 and the width is going to be 1. So 2 times 1 is 2. Then the area of the third rectangle is going to be, here's the length. The area is going to be 5 times 1 because the length is 5 and the width is 1. So that will give me 5 times 1, which is 5. Notice the length of the rectangle corresponds to the y value of the function. And that will lead us into when we start talking about this in more detail later in the semester. So now to estimate the area under the curve, I'm going to add up the areas of all the rectangles. So if I take 5 plus 2 plus 1, the area under the curve is going to be 8. And since the units aren't specified here, we're going to just say in generic form that this is 8 units and x squared, because this is area. So far, up to this point in your math careers, we've studied functions that are one variable only. So, for example, this is something that we're all familiar with. Something like this. We have one variable, it's x, and when we graph it, we put the independent variable, which in this case is your x, on the horizontal axis, and the dependent variable, which is f of x in this case, on the vertical axis, and we have a graph in 2D. When we start getting into 3D, we're going to be looking at functions that are multivariable. And here's an example right here, where I would have a function f, and then I would have a function in terms of x and y, or it could be in with 3 variables. It could be f of x, y, and z. But once we start getting into functions that have multivariables, and we start studying that in terms of calculus and with limits, that kind of calculus is called multivariable calculus. And informally, multivariable calculus can be characterized as the study of the calculus of functions of 2 or more variables. However, before getting into that much depth, first we're going to try to get a handle on studying limits and areas and integration, and this Calc 1 based on just functions with one variable.